the universe. We are going to deal with universe and the earth. So, with this concept of universe formation, theories of formation of universe. Theories of formation of universe, the whole sequence, if I see, of this pattern, okay, the whole thing starts, let's say, in 1915. For this part, you will have to take the running notes. Okay, just a scribbling down. Okay, because there's nothing to dictate in this part, just a timeline. So over here in this case, the idea in the earlier times, I would say, okay, was that of what we call as constant universe, fixed universe. There's no specific name for that. But the idea in the earlier times was that universe is fixed. Whatever is there, it has been created once and it has remained like that forever. Permanency. That was the idea earlier. But then comes the theory of Einstein, which is the general relativity theory. Of Einstein theory, which has been there, this theory also supported the idea of fixed universe. Although the scientific beginning, when we say, we put it with modern cosmology at 1915 only. But there was nothing new in terms of cosmology when Einstein gave his theory. Kyun? Earlier people used to believe the universe is constant. Einstein, when he studied everything with his formulas for general relativity, he supported the idea ki, yes, you were telling correct, I have verified it with my theory that universe is constant. So our modern cosmology begins with Albert Einstein, 1915, and he supported the idea of constant universe. Note it down. So 1915, beginning of modern cosmology, Einstein supported constant universe concept. Okay? Now, after this, moving further forward, what I see is the next development happened in 1929 with Hubble. Hubble. Now Hubble, what he did was, he developed a telescope. And with his telescope, he made a number of observations about the universe, about the space. Okay, still very highly advanced telescopes that are used in the space, they are called as Hubble's telescope, if you may have heard of the name. So this was a revolution basically in cosmology, where Hubble's telescope, so his initial type was a prototype only, but he was able to record a lot of observations from universe. Now the most important thing that he observed, this we will have to understand first, and there is something of a concept. Ab yahan se samajhiyega, okay, this is an important concept which is called as Doppler's effect. A little bit of science, physics. Okay, I'll try to keep it as simple. So Doppler's effect. Doppler's effect, what do we mean by Doppler's effect? The idea we can understand through example. Okay, and one popular example in school textbook also used is an approaching train or receding train. So if you are standing on a platform, yes.
My apologies for interrupting. sharing has some error in it. So written Doppler's effect, but it doesn't show that on the screen share.
Share it is not showing. Okay, just give me one moment. Just wait, just wait. Now, okay. So Doppler's effect. You are standing on a platform, and the train is approaching the platform, continuously whistling. What will happen to the sound that you are listening? Increase or decrease? Increase. It will go on becoming louder as the train approaches you, and just the opposite, as the train leaves the platform, the sound goes on becoming faint. Correct? This is precisely what is Doppler's effect. That is, whenever there is a relative movement between, let's say, there is this source of sound, and you have listener over here. So when the source moves towards listener, or listener moves towards source, matlab they are coming nearer, the frequency of the sound goes on increasing. And likewise, when they are going away, getting separated, the frequency goes on decreasing. That is what is Doppler's effect. Okay? So Doppler effect, what is Doppler effect? Doppler effect, note down, Doppler's effect, change in frequency due to relative movement. Change in frequency due to relative movement between source and observer slash listener. Observer slash listener. Okay? We have written observer and or listener because it is both applicable to sound and light. Sound ka example we are understanding it. This is how it is going to happen. So overall, in this case, if you see this particular example, Doppler effect in light, how it is going to happen. See over here, this is the source, okay, and this is the distance of observer from the source. Now, as the observer moves closer, what is going to happen to these waves? They will start becoming like this, being compressed. All these waves would get compressed. In any wave, okay, this particular part of the wave, I'll draw over here. If we take a wave like this, so wave mein, this is called as wavelength, the length of the wave. This is the length of the wave. And there is something called as frequency. We need not to go into definitions of those, okay, not needed. There is something called as frequency, there is something called as wavelength. Wavelength I have shown you. Now frequency f and wavelength, there is an inverse relationship between them. Means if I say wavelength is higher, which means frequency is lower. Lower wavelength, higher frequency. Okay, that's one thing. This is one relation everyone has to know. And second relation, that is energy, is directly proportional to frequency. Or yahin pe if I include it, I'll make one single relationship like this. Energy is directly proportional to frequency and inversely proportional to wavelength. Yes. So now, everyone has noted down this? So in this case, if I consider this particular idea, light source is over here. So the light source over here, and if the observer reaches here, this whole wave would be compressed like this. If the observer comes more nearer, it would be compressed further. What is happening to the wavelength? Increase or decrease? Wavelength has decreased. Earlier your wavelength was this much. Now your wavelength is only this much. Wavelength has decreased, means frequency has increased. This is what we were dealing with in sound also. When it is coming nearer, the frequency is increasing. Now here you can see it clearly. So same rule applies, that as the source or the observer are moving towards each other nearer, the frequency increases or wavelength decreases. That's the idea what we call as a Doppler's effect. Understood? Now, when you talk about Doppler's effect in light, it is rather very interesting. Doppler's effect, see, this is what is the animation that shows you. Okay, you can see this wavelength decreasing. Next part I'll again deal with it, okay, once I explain you one thing. Now, in this case, when we talk about light, the visible light spectrum, if you see, it is laid out as, we all know this as Vibgyor. Vibgyor everyone knows. This is the visible light spectrum. Now this spectrum is arranged based on their frequency. Isme, out of these, violet has maximum frequency, red has minimum frequency. So as you move from here to here, what is happening to frequency? Decreasing. Frequency decreasing. In terms of wavelength, if I have to write, what will I write? For this, minimum wavelength, or this maximum wavelength, which means moving from here to here, wavelength is increasing. Moving from, wavelength is decreasing, moving from, so wavelength is decreasing, let's see. So wavelength decreases moving from here to here. So, अब इस केस में Vibgyor, what are these? They are colors. Say violet, indigo, blue, green, yellow, orange, red. And beyond these, I have two parts of the spectrum. Over here, I put ultraviolet. And over here, I put infrared. Now, these names themselves are interesting. When you say ultraviolet, what should it signify? Ultra. Even more than violet. What? More than violet. Frequency. Because violet has maximum frequency. So when you say UV, it means its frequency is even more than violet. That's why the name ultraviolet. Like infrared, even less than, inferior, even less than red. What? Frequency again. So I'll say frequency even more than violet, frequency even less than red. These names have been given based on frequency only. And that's how the spectrum is laid out. Now what happens? See, when the frequency or wavelength of the radiation is going to change, its color is going to change. Violet has some specific frequency, let's say x1. So indigo has another frequency, x2. Likewise, okay, over here green has, let's say, x4 frequency. All of them have different frequency. If I change frequency, it means what? What will change? Color will change. Every frequency has a corresponding color. If frequency changes, color changes. Now the most interesting thing happens. When I talk about Doppler's effect in light, let's say there is this observer and there is this source of light. Now this light source is emitting blue light. It is emitting blue light. This frequency. Okay? Let's say x3 frequency. So ये x3 frequency. Now what happens is observer starts moving away from the source. if the observer starts moving away from the source, initially the waves that were reaching over here were like this. Now when the observer has moved here and reached here, these same waves would have to reach like this. What has happened to wavelength? Means frequency decreased. Frequency decreased. Now the frequency that it is emitting is x3, but the frequency that is going to reach over here, okay, maybe, possibly, let's say here we are writing the frequency x5, 6, 7, x7. So let's say the frequency it is emitting is x5, but what is reaching over here would be less than this, would mean let's say x7. So for this observer, light would appear red, correct? So light emitted by the source is blue, but by the time it reaches the observer, it becomes red. So I'll show it like blue, and it reaches over here, and what is reaching over here is red. So this observer actually sees red light. It sees the source, and for me it appears to be red. But is it actually red? It is what rather? Blue. Color itself has changed. Likewise, if it was, let's say, emitting yellow light, kahan pe? x5. And now if the observer starts moving towards it, what can be the possibility? Any possibility? x5 say, x3, x2, any of these, means if it is emitting yellow light, what I may see possibly may be blue. So whenever there would be a movement between source and observer, what you will observe is not actually what it is emitting. It may be more or less than its actual emission. The color changes. That's Doppler's effect in light. Correct? Got it, everyone? So in this case, now if I observe over here, this whole idea, so what is going to happen, everyone see here, in this case, let's take up this one, that is, this is emission. This is the emitted light, yellow. If they are coming nearer, frequency is going to increase. They are coming nearer, frequency is going to increase. Matlab, it can become what color? Any of those? Means this frequency is going to move in this direction. This is the case of approach or recession. Approach or recession between the two. Approach. This is the case of approach. It can be any color based on how fast they are moving towards each other. It can be green or blue or indigo or violet. Or taking the extreme end, I can say it is moving towards which color? Violet. Moving towards violet. Moving towards, it can be anything, but it is moving towards violet. Now violet, these three colors in Vibgyor, out of these violet, indigo and blue, blue dominates. That's why moving towards violet is something what we call as blue shift. Blue shift. Blue shift, how can I express it? What should it translate into? Okay, listen here. I'll give you the time to note down. Don't worry. This blue shift should mean what? Is the color becoming blue? Not necessary. It may become green also from here. Still, I'll call it what? Blue shift. So, blue shift ka means approaching. And approaching means increasing frequency. So, whenever frequency increases, you call it blue shift, regardless of what color it has become. If it was emitting red, it became green. What should I call this? blue shift. If it was emitting red and it became green, still it is moving in this direction. I still call it blue shift, not green shift. There is no term like green shift. And likewise, when it moves in this direction, matlab the frequency decreases. This is the case of approach or recession. Recession. So this is the case of recession. Recession may it is moving towards which dominant color? Red. This you call as red shift, and red shift should mean what? Frequency decrease. Again clarifying, red shift does not mean the color has become red. Give me one example from what to what of red shift which does not involve red. Emitting blue becoming orange. Is this still red shift? Emitting blue receiving green is still a red shift. So red or blue shift has nothing to do with what color the light is. Rather what it represents, whether the frequency has increased or decreased. That is how I have to remember it. Okay, blue shift means increasing frequency, and increasing frequency means the two are approaching. If I say there is a red shift, I should read it as the recession is there and the frequency is decreasing. That's it. So red shift, blue shift, what is the definition? Tell me. Blue shift, what should I say? Try to define anyone. Raise your hand and try to define anyone. Try to define. Red shift. Decrease in frequency, complete it, due to recession between source and observer. Light hai to observer. Okay, define blue shift. But movement you have not defined, na? Which what type of movement? Movement can be this also, na? ये तो Doppler's effect definition हो गया. Okay, blue shift, what I'll say? The increase in frequency due to approaching source and observer, which result increase in frequency बोल दिया हमने. So it has to be defined based on increase or decrease in velocity, frequency due to approach or recession. That's whole of the idea of blue shift and red shift. Understood the idea? Everyone? Note it down quickly and write the definition of both by yourself, red shift and blue shift. Written, everyone? Read blue shift definition, what you have written. increase in frequency, ठीक है. So this red shift and blue shift. Now coming back to Hubble. Hubble, when observed the rays coming from the outer space, he observed the lights coming from number of different stars, and for each and every case, what he observed was a red shift. That is the most important point and turning point in cosmology. Hubble observed a red shift of the light coming from different galaxies. Note it down. Write this statement. Hubble observed red shift in the light coming from different galaxies. So when you say red shift, written from different galaxies. Done? So when you say red shift, Hubble observed a red shift. What should I conclude then? Frequency is decreasing. Means it signifies what case? That moving away from each other. Which means the conclusion was that all the galaxies are moving away from each other. Okay, put a hyphen and mention all the galaxies are moving away from each other. All the galaxies are moving away from each other. Now, this was a big blow to the earlier belief that universe is constant. Because now Hubble has proved it beyond any doubt, because it was from observation, direct observation. Okay, that galaxies are indeed moving. But earlier, indeed, Einstein himself validated the idea that universe is constant. But now Hubble from his observation have shown us that galaxies are moving away. And this is where this was the time when Einstein realized his mistake. And he admitted publicly that this should be the biggest mistake I have made in my life till now, and probably in my future also. That's such a big thing, I somehow missed it. Although his equations, his concept of general relativity, nothing is wrong. Okay, everything has been validated. It's about what he inferred from that. In that, he made a mistake. And then he realized and admitted publicly. But this was a cornerstone I identify in modern cosmology. It changed the complete view of our universe. That our universe rather is dynamic. Should I put it like that? Because earlier we were saying constant. Now we are saying no, it is dynamic. And that's where came the concept of what we call as expanding universe. Expanding universe. This concept now has been called as expanding universe concept. So earlier, which was constant universe concept, now has become expanding universe concept. Understood? So this is expanding universe. And this was the contribution of Doppler. So now in this case, if I have to observe this one, see now, it is decreasing, okay. But now see the color has changed. It started with red and became blue. Correct. Likewise, I go back again, and if I check on this side, started as this one or next one. This part if you see, and this part, see, from blue it is becoming red. You can see the color change. So this is how the color changes with the movement. So in this case, this expanding universe concept when came up, based on that, two different models were proposed on the new concept. Both were based on the new model, and these were one that is Big Bang theory, that we'll deal with later because we have to study in detail, and second that is steady state theory. अब overall idea if I see of expanding universe, how do we understand it? Any good analogy to understand it? Basically, when Hubble is saying that all the galaxies are moving away from each other, that is where a confusion comes. If there are in this space, okay, if there are people, okay, you are sitting over here, we all are here, and now if we try to start moving away from each other, okay, if you move away from me, eventually you are going nearer to him, correct? How is it possible that everyone is moving away from each other? That was one of the question, and that was solved. Even see, such a complex scientific question, but was explained by a simplest of analogy, and that analogy was a inflating balloon. So if you have a balloon on which you have dots, marks put there, if you start inflating it, you will see this effect, that all the points are actually moving away from each other, all the points. So universe from that perspective, from Hubble's perspective, at that time was visualized as a expanding balloon, precisely like expanding balloon on which there are galaxies, and because it is inflating like a balloon, all the galaxies, the distance between them is constantly increasing. Yes. So now came two theories, steady state theory and Big Bang theory. Now what does a steady state theory says? Steady state, constant. But we have already used the term constant universe. That was a different thing altogether. So steady state theory, what it says, the universe expands, but at any given time it maintains all its properties even after expansion. Properties here mainly refer to the density. Ab density agar aap, if you see, what has to happen is, if I take up this space, okay, and 1, 2, 3, 4, 5. If I expand this, just imagining an inflating balloon, it becomes this. What will happen to these? One is over here, another is over here, another is over here, another. Can you say the density of both of these are same? Still there are five, but over larger space. Density has changed. Now if I take up this space over here, do they both look same? No. Here I had, let's say, 5 stars. Here only I have 1 star. They look different. But a steady state theory says no. Even after expansion, it will look like this. Why was it so? A basic idea, because when we see sky with the naked eyes, it roughly looks same to us. Day to day some movement of the constellations and all is going to take place, but nothing changes majorly. So it was based on the common observations itself, and so steady state theory says this happens. What is it? That universe is expanding but always have same properties. How come this is possible? Tell me. Is this even possible? And if, how? I'll remove what I have done over here. This is the original scenario. Now, just think, to create the same scenario, what I need to do, or what I did actually. 1, 2, 3, 4. What have I done? Added, suppose these are stars. I have added stars. What can you tell about universe then? How it can maintain same property? By creation of new stars, by formation of new stars. Steady state theory says that universe do expand but maintains the same properties. How? by formation of new celestial bodies to fill up the space that has been created due to expansion. So due to expansion, the space that is being created, it gets filled up continuously by the creation of new celestial bodies. And that's why at any point of time, if you observe it, it looks precisely same or similar. This is called as steady state model. Got it? It was more popular than Big Bang theory. Okay, at that point of time, it was very popular. Why? Reason I told you. People believed it because this is what they were seeing day to day. They believed that sky looks similar. How come? They have explained it. So steady state model. Steady state model, yes, steady state theory just mentioned there. The universe is expanding, precisely same statement. The universe is expanding. The universe is expanding, but always has the same properties. By formation of new celestial bodies. By formation of new celestial bodies. ठीक है? Yes, everyone? Up to here, simple, straight. This is steady state model. So steady state model, very, very popular model. People do believed it. Scientists followed it. And then the next turnaround, okay, that came in 1964. Now 1964, first try to understand this. This is the most scientific part. So just focus over here. 1964, two scientists, Penzias and Wilson. And this is a real picture, real photo from that time. Okay, Penzias and Wilson. Penzias and Wilson, okay, what they did is they used a huge, large receiver. This is a receiver antenna system. Okay, they constructed it. And what was the purpose? What they were trying to do is they were trying to study cosmic radiations. Cosmic radiations which come from outer space. So their goal was to study cosmic radiations. And for that, they created these receivers. Of course, you can see the size, huge technology of that time. But yes, a perfect system, a perfect antenna system to receive the cosmic radiations. Now, when they started their experiment, they started receiving cosmic radiation, but along with that, they started receiving some noise also. Noise, when I use this word, it's not that sound noise I am talking about. Okay, in electromagnetic spectrum, noise refers to any unwanted signal. Any unwanted signal. And the best example of noise is in fact from the sound only when you tune a radio. At that particular specific frequency, you will have clear sound. But slight here or slight there, you will have this humming sound. That is the unwanted signal also coming. So there you can hear it also, so I can justify the term noise. But in general context, any unwanted signal is called as noise. So here they were receiving cosmic rays, perfect. But along with that, they were receiving some noise. Okay. Now in the present time you don't see it, but in the movies and all, somewhere you must have seen. Okay, in the earlier times, okay, the televisions that people used, the antenna had to be set in a specific direction. And so if it is not so, you will have that noise. That noise is visual noise. I am still using the term noise, but that is visual noise. What needs to be done? Antenna has to be rotated in a specific direction, calibrated, let's call it. They thought it is the same problem. So first, interestingly, what they did was, okay, of course, this large system in an open field, a lot of birds and all. So after few days, the system had a lot of pigeon poop. So they themselves, these two guys, real story, okay, absolutely cleaned whole of the system. This large system, they cleaned it manually by themselves. Probably because of that noise is coming. Noise did not reduce. Then they thought of the same idea, antenna idea. And so they started rotating it. Cosmic radiations are coming from all the direction. Let's check somewhere else. Probably here there is some hindrance, some interference. And somehow, no matter where they rotated it, they were getting the noise. Now this became a big challenge. And so, all this observation data set, they sent it to Cambridge and Harvard. He studied, tell us what it is, what is the problem. We have an operational system, it is receiving cosmic radiation, but what is this noise? Why I am getting it? And that led to accidental discovery of a new type of radiation itself. And that radiation is called as cosmic microwave background radiation, CMBR, cosmic microwave background radiation. A cosmic microwave background radiation, cosmic the term we understand, they received it from outer space. So cosmic. Microwave refers to the frequency range. This is our visible light, UV radiations. And background radiation, why? Because that was a noise. They were getting along with some signal. So cosmic microwave background radiation. Now this cosmic microwave background radiation, this when received, it changed the history. The discovery was definitely attributed to Penzias and Wilson. And most interestingly, they got a Nobel Prize for that. And for that, what they were doing, trying to clean up pigeon's poop. And got a Nobel Prize for that. So it was pure accidental discovery. Okay, they never intended to find anything like this, but they found it. But it changed the course of history of cosmology. And they received Nobel Prize for that. Of what was that changed course? Now CMBRs when received, these CMBRs effectively, if I see these CMBRs, so
we eliminated just about everything. The only possibility was
Penzias and Wilson.
from some outside our galaxy, such as far out of here. We didn't know what to do with that result.
So this is precise the interview clip that I have added. Okay, just to show you what he was saying is, we found it accidentally and we didn't knew what to do with it. This he is telling after winning Nobel Prize. That we didn't knew what to do with this data. What is this? They absolutely had no idea. So over here, these CMBRs, this is what has been the mapping of CMBRs. These thermal traces that you see. This is an actual photograph, although this is not a painting or drawing. Actual photograph, but in space, photographs are taken in a different way altogether. Okay, they take thousands of pictures of different places and they do thermal imaging. There's thermal cameras are there. This looks like thermal cameras in the night vision cameras and all. So these cameras, these thermal cameras, they have clicked a picture and from there has been recreated the universe. So this is a picture where you can see these images, yellow dots which are there, they are showing the CMBR signature. And the most important thing over here is the expanse of CMBR. That you can see CMBR is spread evenly across the universe. It's not just limited to one place or two places. This is for one or another signal, we always say it must have been coming from X star. or some supernova explosion must have happened, the light has come from there. But this was not a one of its kind case, coming from one place. It was coming from throughout the universe. And that's why it became a big thing. What is in there in the universe that we don't know? And it's all pervading everywhere. Now, of course, when this came up, this finding came up, people tried to seek the answer from which theory? Steady state theory, because that was the popular theory of that time. So steady state theory was asked, try to explain it. We explained it maintains its property, this happens, that happens. What is this? You have to explain it. Steady state theory said, no idea. And that is what was the demise of a steady state theory. People said, done. We are going to move towards another theory. That is Big Bang theory. And this was the beginning of Big Bang theory acceptance. That's why a cornerstone. Yes, got it? So 1964, CMBR discovery, Penzias and Wilson. Abhi, how Big Bang theory explains it, I'll come to that a little bit later when we move into Big Bang theory proper. But as of now, this was the demise of what theory? Steady state theory, and beginning of acceptance of Big Bang theory. I'll not say Big Bang theory came after this, because I already told earlier itself Big Bang theory was there, already proposed. But nobody believed that theory. From here, Big Bang theory was accepted as a theory. Now, so everyone up to here, good? It's just a story, nothing more than that. Few concepts here and there. So now, let's talk about this Big Bang theory. And then I'll come to this explanation of CMBR. Big Bang theory. What Big Bang theory says? A Big Bang theory says that whatever matter and energy, I'm using both of the terms, although the books use only matter, but had to be used matter and energy. In fact, NCERT also used only matter, but a proper usage is matter and energy. Why? Because of Einstein. Einstein told us what? Einstein equation. What is Einstein equation? E is equals to mc square, and it basically says that energy and mass are interchangeable. Okay, mass can be converted into energy, which we know from the concept of nuclear bombs, and energy can be converted into mass, which is as of now we have not yet been able to achieve on the earth. So, but Einstein equation says that these two are interchangeable. So whenever definitely I'm talking about mass, I should equally talk about energy. So we are putting it like all the matter and energy of the universe, whatever is in the present time, everything was packed at a single point, like this. Now you are talking about this much of tiny particle or singular atom containing all the mass and energy, whatever is there in the universe now. So its density would be almost infinite. So this was a point of infinite density. This is the beginning point, starting point. And somewhere around 13.7 billion years. So 13.7 billion years ago, this exploded. That explosion is from where this Big Bang term is used. Big Bang. That Big Bang is nothing but referring to this time, this event, when it exploded. And when it exploded, I'll dictate this part. Wait. When it exploded, everything was thrown out in the space. And from that thrown out material only, all the universe has formed. This is simple Big Bang theory, what it proposes. Everything was packed at a single point, then explosion happened, and afterwards everything what you see in the universe has formed out of that only. So overall, this Big Bang theory which has been there, it was a revolutionary idea actually. That's why earlier people were not able to relate with it. How should I know what has happened 13.7 billion years ago? How should I verify it that it happened or not? Not possible. That's why people earlier were inclined towards a steady state theory. It was a simple theory, easy to believe. But now when this theory comes, and as it is a very revolutionary theory, definitely it needed evidences. You will need to prove it now with a lot of evidences. And that's what becomes most important for our exam also. In fact, in prelims, the question has already been asked about the evidences of Big Bang. So Big Bang, the evidences of Big Bang. What are the evidences of Big Bang? The evidences of Big Bang में first तो expanding universe concept. Now expanding universe, how can you explain it? Hubble has established that a universe is expanding, but the question is still existed कि why? Why it is expanding? What causes it to expand? Now here is the answer. If it exploded, everything was thrown out from here. And as everything was thrown out and it is a space only, no friction, the bodies which started moving out, they keep moving out. And so this process continues happening. So it was like this, and from here expanding, 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 and is still present till present, it keeps expanding. The expanding universe concept, it has an explanation over here. That's one thing. But what did I tell you? Which is the most important discovery related to this? CMBR. CMBR is the most important discovery related to that. What is CMBR? Cosmic microwave background radiation. Okay. Now, to understand this, let's try to understand this electromagnetic spectrum. This is called as electromagnetic spectrum. And in this, over here, you can see this is high frequency or low frequency. This is high frequency. Wavelength is less, frequency is high. And this is, so this is low frequency, high frequency. Correct? Now, overall, in this case, the spectrum, how it looks like. सबसे पहला gamma rays come, frequency changes, X-ray, ultraviolet, visible, infra. You can see over here, ultraviolet I said high frequency, VIBGYOR, this is VIBGYOR, visible में VIBGYOR आएगा, and after that infrared, decreasing frequency, less than infrared is microwaves, and even less than that is radio waves. Okay. Now just think, the Big Bang happened. Let's say when the Big Bang happened, this was an explosion. Energy would be radiated out, and this energy would be high or low frequency? High frequency, high energy, because it was a big explosion, huge explosion, unimaginable levels. Frequency is very high, possibly which rays? Gamma rays. So I am saying कि when the Big Bang occurred, which rays must have been emitted? Gamma rays. Now universe started expanding, correct? Plus universe started cooling. पहले तो explosion में बहुत heat रहा होगा, but as it started expanding, cooling would have happened. Plus it is expanding also. What did Hubble's law say? What did Hubble say? Or what does Doppler's effect tell us? If it is expanding, the frequency should decrease. Expanding means moving away from each other. Frequency should decrease. Radiations emitted from the explosion was what? Gamma rays. But as it was expanding, its frequency must have decreased. Would have become, later would have become, and this is the most interesting thing. When scientists speculate, I'll say, that at one point of time, universe must have been filled up with light. Abhi ke liye universe is dark, pitch dark. Outer space is pitch dark. Correct? But during these times, going into outer space, it would have an experience of afterlife. Must have seen in the movies, na, afterlife. Everywhere there is light, you pass a tunnel, after that light is there everywhere. So this must have been that experience. Okay, everywhere light, complete. Then this must have changed too. And this must have changed too. When did we detected it? Here. When Penzias and Wilson detected it, those gamma rays have actually become what? Kyun? Doppler's effect, expansion, reduction in frequency. So when they found these radiations, in which frequency rays they detected it? Microwave. That's why CMBR, cosmic microwave background radiation. Possibly after 1 billion years, if someone detects it, I will have to use what name? CRBR, cosmic radio background radiations. Okay, expansion still is taking place. And if someone would have found it billion years ago, possibly here, they would have found not microwaves, they would have found X-rays. Yes, interesting explanation. So, in this case, how should I define then CMBR? CMBR, try to define, anyone. What are cosmic microwave background radiation? Try to define it. Whatever, no problem, wrong or right. Yes. What is CMBR? What is, matlab, not full form? What is it? Try to define it. Anything. Which is microwave. It's not similar, it is microwave. And anything else? Okay, then this CMBR I should get in my microwave oven also. That also has microwaves only. And how is this different? One part is okay, it's microwaves. Okay, yes, correct idea. Yes, sir. Which has low frequency, correct characteristic. Expansion of universe, okay, one more element. Any try? Anything will do. Decrease in the frequency. ठीक है, okay. That is Doppler's effect. The Doppler's effect definition, redshift definition. What are these radiations? These are the characteristics. You are telling me how formed, decrease frequency, or they are microwave. That anyways is amply clear from the name itself. Cosmic microwave. Telling me. The idea is, what is it? From where did it came, acha? What should be the source of these CMBRs? From where it came historically? From the explosion, Big Bang explosion. These are the same radiations. What should be the age of these radiations? 13.7 billion years. Correct? So the most important characteristic is this only. When I say, what are those? They are the product of what? Big Bang explosion. They were emitted at that time only. Why now their frequency has decreased, but they were emitted at that time. So can I call it, बहुत simple definition is, can I call it residual radiation from Big Bang explosion? Residual radiation from Big Bang explosion. Whatever Big Bang explosion happened, the radiations which came out, which are left now as residues in microwave range, they are CMBRs. Yes? So CMBR is what? Residue. Everyone tell us CMBR is residual radiation from Big Bang explosion. Tell me again, what is CMBR? Residual explosion, residual radiation from Big Bang explosion. Why its frequency decreased? Due to expansion of universe and redshift plus cooling. Cooling se energy reduced. The same frequency. So two basic. If you are asked in the question why frequency decrease, first is expansion and the resultant redshift, and second cooling of the universe, expansion and cooling. So two reasons, okay, why the frequency is now in microwave range. Everyone can get this? Clear? So this is a very scientific proof of Big Bang theory. That's why when we said that it was the time from when Big Bang theory was widely accepted, because it was able to explain CMBR very scientifically, very clearly, which steady state theory was not able to do. So this is the second evidence of Big Bang theory. What are the evidences? First evidence, the expanding universe, and second, that is CMBR. Going beyond that, next one now is when we talk about the idea that the universe is expanding. Okay. Now tell me one thing. If I ask you one idea, one problem, if I give you, there are two people starting from a point and they start moving away from each other. One walks in this direction, another walks in this direction. Their speed of separation is 2 kilometers per hour. Their speed of separation is 2 kilometers per hour. If right now they are 10 kilometers apart, when were they together? Right now they are 10 kilometers apart. Their speed of separation was 2 kilometers per hour. So at what time they were together, or they started? 5 hours ago. Every hour they are getting separated by 2 kilometers. I have not said their velocity, his velocity or his velocity. Speed of separation only I gave you. Every hour they are getting separated by 2 kilometers. So 10 kilometers would mean 5 hours. So time I have calculated as 5 hours. Correct? Got it? Ab, I apply it to this. That these two stars are moving away from each other, which is called as velocity of recession. They are receding. Their velocity of recession is v. They are getting separated by v, this rate. When I measure the two, their distance, the distance between them is d. At what time they were together? Formula. N by 2. Right? यही तो स्पीड का फॉर्मूला है. Velocity is equals to distance upon time. Time is equal to distance upon velocity. What is this time when these two stars were together? now we know all the galaxies started from one point, Big Bang. I can do this for all the galaxies. And I'll get these two galaxies, likewise these two galaxies, likewise these two galaxies. And for that to happen, I need all of these to be at one place. I can calculate the time. Scientists can do that. Velocity of recession is very easy to measure. You have a Doppler's formula for that. Once the scientists calculated the time, it came out to be 13.7 billion years. Using this velocity of recession. So when using the value of recession, they calculated the time when all the galaxies were at one place. This value came out to be 13.7 billion years. This was one way of calculating it. So that is one case. Second, CMBR. Using CMBR also you can calculate the age. How? In the present time, if you want to calculate, you calculate how rapidly the wavelength is changing. Your frequency is changing. You take it back to what? Gamma. And calculate how much time it must have taken. So using CMBR, changes in the frequency rate, scientists calculated the age. Independently, nothing to do with recession velocity now. And most interesting that using CMBR, yahan mila 13.7. When they calculated using these, independent of that, same value. Two independent methods of calculating the age of universe, and both giving you same value. It cannot be coincidence. And so from here, this is most scientific evidence, because that proves that yes, all these stars, celestial bodies were at one place at certain time. So the age of the universe was calculated independently, but both gave us same value at 13.7 billion years. Correct? That is another evidence of Big Bang. So for now, till now, three basic evidences, which would be expanding universe, CMBR, and age of the universe calculated independently by CMBR and using recession velocity. Okay, so abhi aur hai evidences. Okay, but three major evidences which are there. This is the concept of CMBR, the concept of Big Bang. What does it say?